Right now we're going to carry on with the multi-stage amplifiers as in section 6.6. And as usual, when we refer to the textbook as shown on the board, you can mark that I've shown you there in the introductory paragraph. Two or more amplifiers can be connected in a cascaded arrangement. Cascaded means when the output of one amplifier is driving the input of the next amplifier. Now, so they're connected in series with the output of the one amplifier is driving the input of the following amplifier. Each amplifier in a cascaded arrangement is known as a stage. And of course then the basic purpose of a multi-stage arrangement is to increase the overall voltage gain. Alright, first heading there, multi-stage voltage gain. How is it determined? I have to determine the voltage gain of each stage of my amplifier. As you can see there in that specific figure on that page, figure 633. And once I've determined the voltage gain of each stage, then I just multiply each stage with each other to get the overall voltage gain, which is A accent V. That's the overall voltage gain. I can also express the voltage gain in dB as in equation 624, which would be then the voltage gain multiplied with 20 log. The advantage of that is once I've converted it to dB, then I can just add the different stages to get the overall voltage gain. But let's look at a circuit of a multi-stage amplifier. In figure 634 there is a two-stage common emitter amplifier. You should be able to recognize these separate stages. You can see here's one stage. They've also colored it there in your books. There's one stage and next to it there's another stage. Right. So I've got the two stage and I can see that these are common emitter amplifiers. How can I see that it's common emitter? Because the input would be applied there at the base, output is taken at the collector. The remaining is the emitter, AC grounded, and for the second stage, input, which is the output from the first stage, is the input for the second stage. Output again taken at the collector, and the emitter is AC grounded. Alright, so I can see I have a two-stage amplifier, and both these stages are common emitter amplifiers. What I also can see is in this case, and that is not always true, in this specific case that both these stages are identical. I've got the same VCC and you can compare the resistor values. It's a voltage divider. There is R1 and on the second stage it's called R5, 47 kilo ohms. R2, 10 kilo ohms, and on the second stage it's called R6, also 10 kilo ohms. And so I can compare all the components in these two stages and I will see these are two exactly the same amplifiers. Alright, this is just to simplify matters because I want to explain what you really need to know in the two-stage common emitter amplifier so that you can see that it's really not that much different from single-stage common emitter amplifiers. It's exactly the same. I will prove it to you now. Alright, you can mark this in the book, read it there as well. In the textbook there on page 287. Capacitively coupled multi-stage amplifiers. Now that is important. I will talk about it again now. You will see between the two stages there is a capacitor, the same as I had a capacitor on my output to my RL when I had a single stage amplifier. Alright. Notice that both stages are identical common emitter amplifiers with the output of the first stage capacitively coupled to the input of the second stage. Capacitive coupling prevents the DC bias of one stage from affecting that of the other, but allows the AC signal to pass without attenuation because XC is equal to 0 ohms at the frequency of operation. And we know what the word attenuation means. We've discussed that as well. It's when something is reduced, the signal gets reduced as it flows through the signal or through the circuit. Okay, just below figure 614, I've also marked that first paragraph. The loading effect. Now remember, we have discussed the loading effect at various stages. Mark that first paragraph. It says, in determining the voltage gain of the first stage, you must consider the loading effect of the second stage, because the coupling capacitor C3 effectively appears as a short at signal frequency. The total input signal of the second stage presents an AC load to the first stage. Alright. So let's discuss that quickly so that we make sure that you understand what I'm talking about here. Alright, as we've seen, two identical stages, common emitter amplifier we have established, and the two stages are coupled with a capacitor in between. Now if you can recall previously, let me just clean this quickly. Previously, when we only discussed one stage, output was taken from this one stage at the collector, and then via a capacitor it was connected to the load resistor. Is that true? Was that true? That was true, ne? If I ignore this stage, let's ignore this stage. Let's just look at the normal common emitter amplifier as we've done previously. Then the output resistor was connected to that capacitor, wasn't it? That's what we had. That was the load resistor. And we've also determined that the voltage gain, maximum voltage gain, common emitter amplifier was what? RC divided by R accent E. Nah. And then I said, remember, don't go and learn this by heart. You have to go and look at the amplifier that we work with. Nah. I have to go and look, is this formula true for the amplifier that I'm given to work with? So let's go and look at the R accent E at the bottom of the line. Is it true? There is a capacitor that is bypassing R4. So R4 and actually RE then for this amplifier is bypassed. So I would say yes, R accent E is true in this case. Do you agree with me? Yes. Now let's go on top of the line. What did we said? RC. What do I have to check? RC, when we've done the equivalent circuit, would be parallel to what if it is present? Our load, if it is present. Né? If there's not a load resistor, then of course this formula would have been true. But now we've seen I have a load resistor, then I had to calculate R, lowercase c, né? Small letter c, which was RC, or is RC in parallel with RL. You agree? Alright. So, now, let's go to the two-stage amplifier here. Let me just clean this again. Now I removed the load resistor and I connected another identical stage of this amplifier. You could all see that now. But when we started with this single stage amplifier, what did we calculate first over here? The very first thing, Rin at the base, né? What was Rin at the base for this specific type of amplifier? We're talking AC signal. Remember, I want to determine voltage gain, so I'm looking at the AC at this stage. What was it? Beta AC times R accent E, because there's no RE. It's been bypassed. You agree with me on that, né? Alright. Then we didn't stop there. I had to calculate R in total. You remember? R in total then was of course R1 parallel with R2 in parallel with R in at the base. You agree? Then I got R in total, né? So if I ignore this first stage, you agree that I would do the same for the second stage. Nah, so I would work out R in at the base. In this case, it would have been beta AC times R accent E, because RE is bypassed. And then the total input resistance would have been then, in this case, there's the voltage divider. It's just named differently. R5 in parallel with R6 in parallel with R in at the base. You're with me? So I've got here a complete input resistance. Do you agree? Alright, so what am I getting at? If I go and clean this up a bit here. Remember, after this capacitor, my load resistor was connected for a single stage. Now for the multi-stage amplifier, I've got another stage. But that stage has input resistance. No? So, when I go back to my voltage gain formula, the formula still remains the same. It's still RC over R accent E. I still have to go and look at the amplifier. So I'm going to calculate voltage gain of the first stage. RC over R accent E. Is R accent E true? Yes. RE4 is bypassed by C2. So that still remains true. You agree? At the top of the line RC, which in this case is R3, is there a load resistor? There's not a load resistor, but there's a second stage, which has an input resistance. So my first stage, see this input resistance as the load. So I have to go and calculate RC, but in this case R small c is going to be R3. This is RC1. R3 in parallel with R in total of my second stage. Does it make sense? That's the only thing that differs. So when I looked at the single stage, if there's a load resistor, I would have worked out RC, which is RC small letter, which is RC in parallel with RL. Multi-stage amplifier, I work out the voltage gain of the first stage is going to be RC, which in this case is R3, in parallel with the input resistance of my second stage, which is the resistance. Are you all with me? That's all that you have to remember for this specific two-stage amplifier. Okay? So remember, this is a capacitively coupled. So the AC signal goes through and still sees the input resistance of the second stage. Now, remember the purpose of a multi-stage amplifier. I want to increase the voltage gain. Okay, so I have to determine the voltage gain of the first stage. That's what we've done now. Now I'm going to calculate the voltage gain of the second stage. Basic formula, RC divided by R accent E. RC in this case is equal to R7. Is R7 going to be true? Is there a load resistor? Is there a third stage? In other words, that remains true. You agree? And below the line, is RE bypassed or not? RE in this case is R8. There is a capacitor, so that's also true. Voltage gain of the second stage is going to be that. So finally then I have voltage gain of the first stage, voltage gain of the second stage to get the overall voltage gain. A accent V is then going to be AV1 times AV2. That's it. The main thing that you have to remember for a multi-stage amplifier is that the second stage or the third stage acts as a load resistor for the previous stage. That's all you have to remember to be able to work out the voltage gains correctly. Anyway, it is in there on the bottom of the page, loading effects. And then if we go to the next page, when we go there to the next page, you can see here, they say voltage gain at the first stage. All that they've done here now, RC1, as I've told you here, is then R3, which is RC of the first stage, in parallel. Now, you can put the next in brackets as I've shown you there. If you can't see it properly, let's try and zoom it in. I just tried to simplify that to show you what I've done there. That's too much. Can you see what I've done there? I put in brackets the R5, the R6, and R in at the base, which is actually R in total for the second stage. Do you agree? So all that they've done there, they've just put it into one line. Okay, then to calculate AV1 and AV2, as I've discussed with you, you can work through it there again. And then finally, the overall voltage gain is AV1 times AV2. If we turn not turn the page, at the top of that page, actually, they've shown you the equivalent AC equivalent circuit. There's the first stage, and here's the input resistance of the second stage that you have to use then as the load resistor. Remember, this was RC for the first stage. So that acts as the load resistor for the second stage. That's what they tried to explain to you there. Alright, the last thing here is, remember this amplifier that we've discussed was a capacitor coupled amplifier. Now you also get the multi-stage amplifier, which is direct coupled multi-stage amplifier. The direct means there's no capacitor between the two stages. And now can you see what makes it different? Here's my first stage of amplifier. Up to there's my first stage. Can you see? There's my voltage divider. There's my input. Output is taken at the collector. And here then normally via a capacitor it would have been connected to a load resistor. But now I'm leaving out the capacitor. That's why they call it now a direct coupled amplifier. So now the capacitor is left out. So you can see already in the second stage there's no voltage divider. Why? I don't need the voltage divider because VC1 is also, because there's nothing in between, is also equal to VB2. So the first stage VC provides VB of my second stage because there's no capacitor that blocks the DC. No capacitor that blocks the DC. In other words, there's going to be no voltage divider. It's just directly coupled, and the first stage provides the voltage here for the second stage. So VC1 is going to be equal to VB2. Alright, so if we go back to the textbook, I want you to mark some things there on the direct coupled . Notice that there are no coupling or bypass capacitors in this circuit. The DC collector voltage of the first stage provides the base bias voltage for the second stage. Because of the direct coupling, this type of amplifier has a better low frequency response than the capacitively coupled type, in which the reactance of the coupling and bypass capacitors at very low frequencies may become excessive. The increased reactance of capacitors at lower frequencies produces gain reduction in capacitively coupled amplifiers. That's the advantage, no? We have assumed that the frequency doesn't influence the amplifiers that we've discussed so far, but in a later chapter we will discuss the influence of frequency on my amplifier. Alright. But here's the first mention of that anyway. The second paragraph, direct coupled amplifiers can be used to amplify low frequencies all the way down to DC, 0 Hertz. DC has no frequency, straight line, without loss of voltage gain because there are no capacitive reactances in the circuit. The disadvantage of direct coupled amplifiers, on the other hand, is that small changes in the DC bias voltages from temperature effects or power supply variations are amplified by the succeeding stages, which can result in a significant drift in DC levels throughout the circuit. Remember now, as say there are influences, outside influence that varies this voltage on the output here, then this voltage is also going to vary because of temperature and whatever. So I may get a drift in later stages as I carry on because of this voltages that may vary, because I'm using the output voltage of the one stage to drive the input of the second stage. Previously it was blocked, and then I had another voltage divider, for instance. Alright, so that's the disadvantage of this amplifier. Alright, that's the multi-stage amplifiers. All those points again. And now you have to do basic problems from 29 to 35. Please go and do so that you can test yourself to see that you understand the work. If you don't, so that we can discuss it again and make sure that you understand the work.